Hi everyone, welcome to the sixth video in the series of group theory. This video is going to talk about group homomorphism. We will see what is meant by group homomorphism, what is going to be the kernel of a homomorphism, and solve problem related to homomorphism. Come on, let's get started. First, we will define what is meant by a group homomorphism. Let us say, suppose we are going to have two groups, one G with a binary operation star, the other one G dash with a binary operation delta. So these two are going to be group. Now let f be a function that is going to be mapped from G to G dash. That is, it takes elements of G and maps it to elements of G dash. Then f is said to be a group homomorphism if it satisfies the condition f of A star B is equal to f of A delta f of B, where star is the binary operation in the first group and delta is the binary operation in the second group. So say for suppose I have this to be my G with respect to star, and I have one more quantity over here which is going to be G dash the group with binary operation delta. Now there is going to be a function f that is going to go from all the way from G to my G dash. Now if I am going to pick any two elements over here in my G called as A and B, this A will go on f and produce an f of A, and this B will be transformed by this f to an f of B. Now if we take these two elements and consider the binary operation over here, the closure of it will be your A star B, and if it is getting transported by f, what will happen to this quantity f? Now this has to go to f of A, the image of your A, and this star is now being acted by this binary operation delta, and now this becomes f of B. So now if this is going to be true, when f acts on this element and produces this as your output, then this function f will be termed as a group homomorphism. It's to be made sure that all the ways it's not going to be true. So for the cases when this holds true, then such a function f will be referred as group homomorphism. Next, moving on, we will see what is going to be the definition of kernel of homomorphism. As we said, let G with respect to my star and G dash with respect to delta be two groups. Now this G has an identity element, let me mark it as E, and this G dash as an identity element, let me mark it as E dash, and there is going to be a function f that transports elements from your G to your G dash. What we mean by kernel is, the kernel of a group homomorphism is defined as the collection of all the elements A that belong to G such that their images f of A gets mapped to E dash. So when I am able to pick elements over here so that when they get transported, they get mapped to this E dash, then the collection of all such elements over here will be referred as kernel of f. So when I take this A and go with the function, and this output f of A is nothing but the identity element E dash of your G, if all the collection of elements we are going to take are going to be mapped down to E dash, such a collection will be referred as kernel of f. Now having got the definition for group homomorphism and then your kernel, we will try to apply them to problems. Consider the groups R with respect to plus and R star with respect to star to be two groups. Like as we said over here, the first one is going to be your R, the set of real numbers, and addition is going to be the binary operation. What happens over there? R star. What does R star means? It is going to be the set of all real numbers but exclusive of the element called as 0. So it is non-zero real numbers. So R star is nothing but non-zero real numbers. So I have this as my collection R star, and what is the binary operation here? Multiplication is going to be the binary operation over here. And now we have the function f, which transports elements from R to R dash in such a way that f of a is going to be 2 power a. You pick an element a, it transports here, and where it gets mapped to? It gets mapped to 2 power a. So we will have to check if this is going to be a group homomorphism. Now let me pick two elements from over here. Now I know that image of a is 2 power a, and if I take one more element called as b, what will be the image of b? It will be 2 to the power of b. What is the binary operation over here? It is plus. So I take a plus b. What will be the binary operation here? It is going to be dot. What is going to be dot? 2 power a dot 2 power b. Now if my function f can act on this a plus b and produce this 2 power a dot 2 power b, then I can say that f is going to be an group homomorphism. Are we ready? Yes, we can begin the checking now. Now let me take two elements over here, which is going to be a and b, and I am going to compute f of a plus b. By the definition of the function, how we have defined f of a? 2 power a. So what will be f of a plus b? It will be 2 power a plus b. What is going to be the power law over here? 2 power a plus b can be written as 2 power a product 2 power b. And this is nothing but 2 power a is nothing but your f of a. 2 power b is nothing but your f of b, and what is there in between? It is going to be the binary operation from over here. So I have started with f of a star b, and I have landed with my f of a delta f of b. So in which case I prove that the f is able to transport quantities of a plus b to the second binary operation as product of elements. Therefore, f is a homomorphism. Now coming to the second part, what is going to be kernel of f? So I know that kernel of f is the collection of all elements a that belong to my R in such a way that f of a must be equal to the identity element e dash, and your e dash belonging to your R star. Okay, R is going to be the first set, R star is going to be your second set. Now what is going to be the identity element for your multiplication with respect to R star? I know that with respect to multiplication, what acts as an identity element? Any element multiplied with 1 gives me back the same element, is going to give me back my a, and a dot 1 equal to 1 dot a is my a. So which acts as an identity element? 1 acts as an identity element for multiplication. So your e dash is nothing but 1, which is present over here in this R star. Now I need to check what all elements over here, a kind of a, b, c, that will have its image as 1. Meaning that when I rise 2 to the power of a that has to get mapped to the element 1. So any element a which I am going to pick from R has to make sure that on applying the function f that gets transported to 1. So which element is going to have 2 raised power a to be mapped to 1? Yes, a equal to 0 is the only real number, so that I can write 2 power 0 is equal to 1. So my kernel of f will contain a single element alone, and the element is nothing but 0. If we have one or more such elements that gets mapped to a, the collection all of them will be put over here and referred as f. But this condition 2 power a equal to 1 can be satisfied by only one of the element, which is going to be 0. So kernel f consists of just one element, that is 0. I hope the problem number 1 is clear. We will move on to one more problem to make sure that the concept of homomorphism is recorded perfectly. Now let R with respect to plus, which means positive real numbers, with respect to multiplication be one group, and the other group be your R, the set of real numbers, with respect to addition. I take a function f from over here, the positive real numbers, to my real numbers through my f in such a way that f of x is marked to log x. So I pick a x from over here, whereas your f of x taking this x to, it takes it to log x base 10. So how to prove that it is going to be in homomorphism? So let me pick two elements x and y from over here. What is the binary operation? The binary operation is dot. So the closure is x dot y. Where is x getting mapped to? This will be mapped to your f of x. And where will your y get mapped to? It will get mapped to f of y. What will be the closure of these two with respect to the binary operation? It has to be f of x plus f of y. Now, if my function f on applied to the closure is able to transport it to f of x plus f of y, then I can call this f to be a homomorphism. Come on, let us check. So let me take two elements, f of x dot y. How we have defined the function f of x? It is going to be log base 10 of x. So you have log 10 base x product y. And we know that log ab can be written as log a plus log b, in which case this can be written as log x base 10 plus log y base 10. And furthermore, this log x is nothing but our function f of x, and this log y is nothing but our function f of y. And what is the binary operation over here? It is going to be plus. So see that I started with a binary operation which is going to be there from your first group, and I ended up with a binary operation in my second group. So I know that f of x star y is the same as your f of x delta f of y. Therefore, we can conclude that f is going to be an homomorphism. So these two examples must have provided you with a clear idea what a homomorphism is. Happy learning, keep learning.